November 24, 1944, over the outskirts of Tokyo, Japan. On this date, 111 Boeing B-29 Superfortress bombers departed from bases in the Mariana Islands for the first strategic raid against the Japanese homeland from that theater, with 88 aircraft reaching the Tokyo area to target the Nakajima Musashino aircraft engine plant at altitudes between 27,000 and 32,000 feet. Japanese military planners had anticipated medium-altitude incursions similar to those from Chinese bases, where bombers operated below 20,000 feet and remained susceptible to interceptors such as the Nakajima Ki-43 and Kawasaki Ki-45 fighters. In contrast, the B-29's pressurized cabins permitted sustained crew performance at elevations where Japanese aircraft experienced significant reductions in climb rate and maneuverability, leading to only limited engagements. This disparity yielded minimal effective interceptions, with Japanese forces claiming just one B-29 damaged. The Central Fire Control System augmented defenses by synchronizing remote turrets through analog computers for accurate .50 caliber gunfire. This operation initiated a transformation in strategic bombing doctrine, revealing critical deficiencies in Japanese air defense networks. February 1940, Boeing facilities in Wichita, Kansas. Engineers examined blueprints on a drafting table, computing cabin pressure differentials to support operations above 25,000 feet. The hum of calculating machines fills the design room as specifications emerge for what would become the most advanced bomber of the war. The United States Army Air Forces projected bomber ceilings restricted to 25,000 feet without pressurization, mirroring B-17 Flying Fortress constraints. However, the B-29's implementation achieved over 30,000 feet, confounding Japanese assessments that aligned defenses with lower operational profiles. General Henry H. Arnold, Chief of the Army Air Forces, authorized the initiative in official correspondence dated February 5, 1940, underscoring requirements for extended-range missions in the Pacific Theater. Arnold recognized that defeating Japan would require bombers capable of reaching targets from distant bases across vast oceanic expanses. The pressurization mechanism employed sealed compartments sustaining an internal equivalent of 8,000 feet at external altitudes up to 30,000 feet, complemented by 4 Wright R-3350 duplex Cyclone engines, each delivering 2,200 horsepower at takeoff. Prototype evaluations occurred in 1942, wind tunnel facilities at Wright Field, Ohio. Per declassified Army Air Forces specification XR-29, the design mandated pressurized crew compartments to enable high-altitude operations without individual oxygen masks for extended duration, as outlined in procurement records dated January 1940. This represented a revolutionary departure from existing doctrine. This advancement transitioned operations from unpressurized formations vulnerable to crew fatigue and hypoxia to secure high-altitude groupings, thereby diminishing crew vulnerabilities and extending mission endurance beyond 10 hours. By mid-1943, monthly B-29 assembly rates approached 100 aircraft from Boeing's Wichita plant alone, whereas Japanese production of comparable high-altitude fighters yielded fewer than 500 units annually across all manufacturers. The developmental stage established groundwork for campaigns that Japanese intelligence evaluations fundamentally undervalued, prioritizing defenses against traditional bomber susceptibilities rather than revolutionary capabilities. Specifications demanded a bomber capable of 400 miles per hour at altitude, yet initial tests in September 1942 revealed critical engine overheating issues, resolved through iterative modifications including improved cowling and cooling systems. Arnold's strategic memos emphasized the Pacific's vast distances, necessitating operational ranges exceeding 5,000 miles round-trip. Prototypes, designated XB-29, underwent rigorous assessments at Boeing Field, confirming pressurization's role in maintaining crew alertness during prolonged flights over water. Japanese pre-war intelligence, reliant on observations of earlier United States designs like the B-17 and B-24, failed to anticipate this technological leap, calibrating interceptors for engagements below 25,000 feet where unpressurized crews could still function. Production ramps at Wichita involved over 10,000 workers operating 2 shifts, achieving manufacturing efficiencies that contrasted sharply with Japan's fragmented, dispersed production system. This disparity foreshadowed operational imbalances where technological superiority would compound industrial and logistical advantages. 1942 through 1943, Sperry Gyroscope Company Laboratories, Great Neck, New York. Technicians in white coats adjust analog computers, connecting remote sighting stations to turret mechanisms for synchronized defensive operation. The smell of machine oil mixes with electrical ozone as firing circuits undergo testing. Adversaries anticipated manually operated armaments akin to those on B-24 Liberators, where individual gunners aimed independently. The B-29's automated system delivered enhanced precision against approaching fighters, exceeding projections by Japanese strategists who expected fragmented, uncoordinated defensive fire. Sperry engineers, documented in United States Army Technical Bulletins TB 430118, incorporated fire control radar integrations unprecedented in bomber design. The apparatus comprised 4 remotely managed turrets, 2 dorsal and 2 ventral, equipped with 1250 caliber M2 Browning machine guns utilizing gyro-stabilized optical sights and electromechanical lead computing algorithms. Evaluations at Aberdeen Proving Ground involved simulated combat scenarios replicating high-speed fighter assaults from multiple vectors. The Central Fire Control Director furnished ongoing computational resolutions to the fire control ballistic equation, accounting for target speed, range, and deflection angle, as recorded in Boeing technical documentation dated November 1943. Mechanized targeting mitigated human operator inaccuracies inherent in manual systems, interfacing seamlessly with pressurization to permit gunners' functionality within sealed, temperature-controlled environments while turrets operated externally in -50-degree temperatures at altitude. Preliminary assessments at Eglin Field indicated 20% superior accuracy over manual configurations, a differential that Japanese fighter aviators would confront during 1944 incursions. This component fundamentally redefined bomber protective strategies, establishing the B-29 as an autonomous defensive entity independent of conventional fighter escorts that dominated European theater doctrine. Engineering efforts at Sperry focused on complex parallax corrections, accounting for physical offsets between remote sighting stations and gun positions, alongside sophisticated ballistic adjustments for gravity drop and crosswind deflection. Lead computations predicted target trajectories based on observed angular velocity, enabling preemptive fire placement. Integration with early radar systems enhanced night operations, a capability feature absent in prior bomber designs. Army Air Force's reports noted initial synchronization challenges between sighting stations and turrets, addressed through refined analog circuitry and improved servo mechanisms. The system's innovative design supported multiple gunners controlling turrets interchangeably from 5 sighting stations, optimizing crew tactical roles during engagements. In stark contrast to Japanese defensive setups, which relied exclusively on visual aiming with manually trained guns, this automation provided an overwhelming technological edge. Production incorporated General Electric electrical components and Westinghouse hydraulic systems, with over 3,000 complete fire control units fabricated by war's end. Japanese doctrine, emphasizing close-range ramming tactics against bomber formations, catastrophically underestimated the system's effective range of 1,000 yards and combined rate of fire exceeding 9,600 rounds per minute, leading to elevated attrition rates in early air-to-air encounters. April 1944, forward airfields in Chengdu, China, under the ambitious Operation Matterhorn logistics chain. Ground personnel in sweat-stained coveralls maintained temperamental R-3350 engines under severe supply constraints, carefully arming aircraft with 5,000-pound general-purpose ordnance for preliminary combat missions. American commanders forecasted substantial operational losses due to logistical hurdles and anticipated heavy Japanese fighter opposition. Japanese intelligence units projected constrained operational reach from isolated Chinese installations, fundamentally disregarding the B-29's extraordinary 5,130-mile maximum range, facilitated by pressurization efficiency and fuel capacity. Brigadier General Haywood S. Hansel, commanding officer of the 21st Bomber Command, appeared prominently in mission planning directives. The inaugural combat sortie on June 5, 1944, targeted Bangkok Railway marshalling facilities in Thailand. Pressurization technology supported sustained 25,000-foot bombing runs, effectively circumventing certain categories of ground-based anti-aircraft defenses calibrated for lower-altitude attacks. B-29s functioned operationally at elevations beyond effective Japanese fighter interception capability, according to official findings in the United States Strategic Bombing Survey compiled in 1946. Strategic relocation to Pacific Island bases subsequently alleviated dangerously exposed Chinese logistics networks, magnifying the revolutionary technology's operational scope and sustainability. By October 1944, initial assault missions on Kyushu industrial targets demonstrated Japanese interception efficiencies below 10%, clearly indicating systematic unpreparedness for threats operating at extreme elevations. Early operational deployments corroborated the integrated system's tactical efficacy, preparing American forces for sustained assaults on the Japanese mainland that would fundamentally challenge existing aerial defense paradigms. Operation Matterhorn involved complex forward basing operations in both India and China, requiring over 20,000 tons of supplies airlifted monthly over the Himalayan hump route. Hansel's operational orders prioritized precision strikes on industrial manufacturing targets. The historic June 5 Bangkok raid saw 98 B-29s dispatched from Chinese bases, with 77 successfully reaching the objective area, dropping 368 tons of high explosive and incendiary bombs. Persistent mechanical issues, including dangerous engine fires caused by magnesium crankcase ignition, accounted for initial mission aborts, but pressurization systems ensured crew safety during prolonged ascents to operational altitude. Japanese air defense responses included heightened alert statuses and increased fighter patrols, yet interceptors like the Ki-44 Shoki struggled fundamentally at operational heights above 28,000 feet. Complex logistics severely strained United States resources and personnel, ultimately prompting strategic shifts to newly captured Mariana Island bases. This initial operational phase accumulated 47 combat missions by January 1945, inflicting moderate industrial damage while conclusively validating high-altitude bombing tactics. Stark contrasts emerged in fuel consumption metrics. B-29s required 7,000 gallons of high-octane aviation fuel per combat sortie versus severe Japanese constraints on aviation fuel production capacity that would worsen throughout 1945. 1943 through 1944, massive Boeing assembly plants in Wichita, Kansas, and Seattle, Washington. Sprawling assembly lines fabricate aluminum fuselages in methodical progression, with thousands of skilled personnel carefully affixing pressurized cabin seals amid accelerated wartime production schedules. The constant riveting creates thunderous noise as three-shift operations proceed around the clock. Japan depended entirely on decentralized, modest-volume aircraft fabrication dispersed to prevent bombing damage. United States industrial yields escalated dramatically to 300 B-29s monthly by late 1944, far surpassing Japanese defensive adaptation capabilities. Boeing executives, prominently noted in comprehensive War Production Board statistical analyses, systematically reduced labor hours per individual unit from an initial 157,000 man-hours to below 20,000 through standardization and improved assembly techniques. Aggregate wartime output surpassed 3,900 complete aircraft. Supporting supply chains encompassed extensive overseas depot networks, facilitating 3,000-mile transoceanic missions from forward Pacific bases. 3,970 B-29s constructed during complete wartime production cycle per official United States Army Air Forces archives maintained at Maxwell Field. Extensive manufacturing capacity sustained prolonged strategic offensives, with pressurization technology significantly curtailing crew attrition from debilitating altitude-related physical strains. Japanese total aircraft fabrication reached approximately 76,000 units for the entire Pacific conflict across all types, completely dwarfed by focused United States heavy bomber production volumes in a single category. Manufacturing asymmetries guaranteed overwhelming B-29 numerical proliferation, fundamentally redefining anticipated operational loss ratios. Wartime industrial mobilization engaged 4 primary production facilities: Wichita, Renton near Seattle, Marietta in Georgia, and Omaha, Nebraska, collectively producing multiple variants including the improved B-29A model. Dramatic efficiency gains stemmed from rigorously standardized interchangeable components and intensive workforce training programs, systematically reducing manufacturing defects. Complex logistics networks incorporated submarine-delivered critical parts to isolated Pacific outposts when surface shipping proved vulnerable. In stark comparison, Japan's peak aircraft output reached just 2,180 units in 1944, severely hampered by critical resource shortages, including aluminum, magnesium, and rubber. Complete B-29 assembly operations required coordination among 1,400 specialized subcontractors, providing everything from instruments to landing gear, dramatically contrasting with Japan's increasing reliance on small dispersed workshops as factories faced bombing. This unprecedented industrial surge enabled operational deployment of over 1,000 combat-ready aircraft by mid-1945, completely overwhelming available Japanese interceptor allocations. Engine production alone exceeded 16,000 R-3350 units from Wright Aeronautical facilities. The fundamental imbalance highlighted total industrial mobilization's decisive role in achieving strategic dominance. Additional facilities at Bell Aircraft in Marietta and Martin in Omaha contributed substantial production numbers. Manufacturing involved over 55,000 workers at peak employment across all plants. Quality control procedures required 16-hour flight testing before acceptance. Modification centers at Birmingham and Oklahoma City incorporated combat feedback, adding improved radar and defensive armament. Production costs averaged $639,000 per aircraft, substantial but manageable within wartime budgets. Material requirements included 12 tons of aluminum alloy per airframe. Manufacturing bottlenecks, initially centered on pressurization seals and fire control computers, resolved through dedicated subcontractor development. October 1944, newly constructed forward airfields on Saipan and Tinian Islands in the Marianas Chain. B-29s carefully maneuver on freshly graded coral runways, powerful engines laboring against oppressive equatorial heat and humidity conditions. Ground crews work in temperatures exceeding 95 degrees. Japanese strategic leadership presumed continued isolated threats exclusively from distant Chinese bases. Revolutionary Mariana's forward positioning enabled direct 1,500-mile strikes against the Japanese home islands, fundamentally disrupting existing radar early warning surveillance networks. Major General Curtis E. LeMay, assuming operational command in January 1945, appeared prominently in revised strategic planning records. Initial base installations accommodated 180 B-29s at operational outset, with expansion planned. Central fire control systems underwent intensive formation-level tactical evaluations under realistic combat conditions. Mariana's strategic bombing campaigns officially initiated with combat sorties on November 17, 1944, as documented in comprehensive Air Force historical overviews. Dramatically reduced transit distances, minimized cumulative technical malfunctions and engine failures, significantly bolstering overall system operational dependability and mission completion rates. As operational altitudes progressively increased toward 30,000 feet, Japanese interception endeavors declined precipitously, with available fighters fundamentally incapable of sustained closure rates at extreme elevations. Advanced forward basing operations intensified the strategically unanticipated aspect of high-altitude bomber resilience against conventional defenses. Intensive construction of Saipan airfield complexes involved over 11,000 United States Navy Seabees, successfully completing multiple 8,500-foot reinforced runways by October 1944. LeMay's arrival in January 1945 dramatically shifted operational focus toward intensified maximum effort missions. Initial combat deployments from Isley Field numbered 120 operational aircraft by December. Sophisticated radar evasion tactics exploited inherent high-altitude operational advantages, with reliable pressurization systems supporting grueling 10-hour combat missions. Japanese desperate counter-raids on Saipan facilities destroyed 11 B-29s on the ground during November attacks, prompting enhanced perimeter defensive measures. Massive logistics operations included 500,000 barrels of high-octane aviation fuel stockpiled in underground storage. This strategic transition cut average mission flight times by half compared to China operations, dramatically improving monthly sortie rates to 1,200 by spring 1945. Base construction required moving 13 million cubic yards of coral. Runway surfaces used coral mixed with asphalt binder capable of supporting 140,000-pound aircraft weights. Hardstand parking accommodated 120 aircraft per field. Maintenance facilities included specialized engine overhaul shops. Fuel storage employed both above-ground tanks and underground caverns for protection. Ammunition bunkers held 12,000 tons of ordnance. Housing facilities supported 20,000 personnel per island. Water desalinization plants produced 500,000 gallons daily. Hospital facilities treated 2,000 patients. Weather stations provided critical forecasting. Communication centers maintained contact with Pearl Harbor and Washington. Tinian's North Field became the war's largest operational bomber base, with 4 parallel 8,500-foot runways supporting 265 B-29s. The 303rd Bombardment Wing arrived in January 1945, adding to the 73rd Wing already operational. Supply ships delivered 45,000 tons monthly. Maintenance achieved 85% aircraft availability rates. Navigation training emphasized celestial techniques for overwater flights. Crew rest facilities provided respite between missions. Combat losses from Mariana's bases totaled 485 aircraft through war's end. November 1944, 21st Bomber Command, Forward Headquarters, Guam Island. Senior staff officers meticulously scrutinized detailed reconnaissance maps, carefully delineating optimal high-altitude approach trajectories to bypass identified Japanese anti-aircraft gun emplacements around Tokyo. Existing defenses remained oriented exclusively toward low-level incursions, similar to the famous April 1942 Doolittle raid. B-29s scheduled unprecedented daytime precision bombing at 28,000 feet operational altitude. Colonel Wyatt D. Fairbanks commanded the veteran 73rd Bombardment Wing assigned to the operation. Individual sorties equipped with 2,000-pound general-purpose bombs for maximum structural damage. Pressurization systems maintained critical bombardier precision during extended target approaches. Operation San Antonio 1 assaulted the Nakajima Musashino aircraft engine manufacturing plant on November 24, 1944, from official operational mission logs. Tactical integration of central fire control systems for coordinated protective defensive barrages effectively dissuaded Japanese fighter pursuits during bomb runs. Of 111 B-29s launched from Saipan, 88 successfully attained primary objectives, with 0 combat casualties from direct adversarial defensive actions, a remarkable achievement. Extensive preparatory measures clearly accentuated overwhelming technological superiorities against anticipated operational hazards. General Hansel's planning staff meticulously analyzed photographic reconnaissance from specialized F-13 variants, identifying problematic cloud cover risks over targets. Mission planning emphasized tight formation integrity for mutual defensive protection. Calculated ordnance loads totaled precisely 2.6 tons per individual aircraft. Intelligence reports consistently underestimated Japanese radar detection capabilities, leading to tactical route adjustments. Detailed crew briefings stressed critical pressurization protocols to counter potential hypoxia risks during extended high-altitude operations. This historic mission, involving the 73rd Wing's 4 bomb groups, 498th, 499th, 500th, and 501st, marked the decisive strategic shift from peripheral targets to core Japanese industrial infrastructure. Weather forecasting predicted 60% cloud cover, necessitating radar bombing techniques. Navigation plans required 6-hour outbound flights. Fighter escort proved impossible given range limitations. Formation assembly occurred at 5,000 feet before climbing to operational altitude. Radio silence procedures prevented Japanese early warning. Bombing altitude selection balanced accuracy against defensive considerations. Target folders identified 40 critical aim points within the factory complex. Intelligence estimated 200 Japanese fighters available for defense. Contingency plans designated alternate targets if weather prevented primary attack. Bombardier training emphasized the revolutionary Norden bombsight operation at extreme altitude. Lead bombardiers received specialized instruction, practice missions over truck-validated procedures. Ammunition loads included 9,600 rounds of .50 caliber per aircraft. Gunner positions assigned overlapping defensive sectors. Emergency procedures covered depressurization scenarios. Ditching plans marked submarine rescue positions. Mission briefings on November 23rd revealed the historic nature of the operation. Crews understood this represented the culmination of 3 years' development. Maintenance personnel conducted final inspections. Weather officers provided updated forecasts. Intelligence officers distributed target photographs. Chaplains offered services. Pre-flight meals provided high-protein nutrition. Equipment checks verified oxygen system functionality. Engine run-ups confirmed mechanical readiness. November 24, 1944, skies over Tokyo Bay at 32,000 feet. B-29 bomber groups ascend methodically through persistent overcast conditions, crew compartments pressurized for optimal operational efficacy. Oxygen systems maintain consciousness in the thin atmosphere. Japanese ground-based detection systems successfully identified incoming intruders, yet available fighters proved completely ineffective at engaging elevated bomber formations. Combat personnel from the 73rd Bombardment Wing appeared prominently in detailed post-mission tactical evaluations. 24 bombers successfully released bomb payloads on the primary target through gaps in clouds. Central fire control systems countered sporadic fighter approach attempts with concentrated defensive fire. Limited structural destruction achieved against the hardened factory, yet no B-29s succumbed to Japanese defenses via comprehensive United States Strategic Bombing Survey analysis. Elevated operational altitude safeguarded aircraft effectively, facilitating subsequent strategic engagements. Japanese fighter aviators documented profound astonishment at observed bomber velocities and extreme operational elevations in post-flight debriefing accounts. The incursion exposed previously unexplored critical gaps in protective defensive measures. Of the 111 B-29s departing Saipan, persistent mechanical issues aborted 17 aircraft, with 88 proceeding to target areas. Dense cloud cover at 90% coverage compelled radar bombing techniques for most aircraft, yielding 48 tons of high explosives on the Musashino plant. Japanese Ki-44 Shoki and Ki-61 Haiyan fighters launched 125 defensive sorties, achieving minimal intercept contacts. B-29 defensive gunners reported no confirmed shoot-down claims, but the overall raid incurred just one total loss to catastrophic engine failure. Subsequent bomb damage assessment analysis revealed 27% plant structural damage, insufficient for complete operational shutdown, but clearly demonstrative of strategic reach capability. The flight required 14 hours round trip from Saipan. Crews endured temperatures of -40 degrees at altitude despite pressurization. Navigation relied on celestial fixes over featureless ocean. Landfall occurred at the Boso Peninsula. The bomb run lasted 8 minutes. Flak bursts appeared 5,000 feet below formation altitude. Fighter attacks concentrated on trailing aircraft. One B-29 sustained minor damage from 20mm cannon fire. Fuel consumption matched predictions at 6,800 gallons average. Return flights faced 60-mile-per-hour headwinds. 2 aircraft diverted to Iwo Jima with mechanical issues. Bombing results showed 16 direct hits on factory buildings. Fires burned for 3 hours. Reconnaissance confirmed damage to assembly halls. Japanese production decreased 15% for 2 weeks. Civilian casualties totaled approximately 80 killed. Anti-aircraft fire expended 800 rounds without hits. Fighter pilots reported difficulty maintaining formation at altitude. Several Japanese pilots experienced hypoxia symptoms. Ground observers noted contrails marking bomber paths. Post-mission debriefings identified issues with bomb site calibration. Cloud cover exceeded forecasts. Radar bombing proved less accurate than visual methods. Some crews reported central fire control malfunctions. Engine overheating occurred in 3 aircraft. Recommendations included improved weather forecasting and increased ammunition loads. Despite limitations, the mission validated operational concept. Command declared it a strategic success given 0 combat losses. Late November 1944, Japanese Army Air Force interceptor bases surrounding Tokyo metropolitan area. Fighter aircraft launch urgently, pilots recording severe altitude constraint limitations in operational journals. They anticipated straightforward conventional engagements based on previous experience. Harsh reality demonstrated fighters like the Nakajima Ki-84 Hayate ascending desperately but remaining unable to maintain effective pursuit against B-29 formations. Japanese command staff appeared in urgent Imperial General Headquarters strategic reviews analyzing the unexpected threat. Anti-aircraft artillery batteries hastily recalibrated for higher trajectory angles, yet firing precision at 30,000 feet remained severely deficient. Initial desperate ramming maneuver tactics were observed and recorded by American gunners. Japanese interceptor fighters executed merely 40 actual assault attempts against 184 radar detections from engagement statistical archives. Fundamentally ineffectual countermeasures necessitated emergency resource reallocations, severely burdening already strained supply networks. B-29 defensive armaments accounted for 74 adversary aircraft destroyed or damaged in preliminary operational stages. Inadequate defensive safeguards disclosed inherent susceptibilities to sophisticated American bomber technologies. Imperial Headquarters emergency directives shifted elite fighter units from Manchurian occupation duties, critically depleting strategic reserves. Anti-aircraft gun batteries, numbering 330 heavy weapons around Tokyo alone, fired approximately 2,400 rounds ineffectively during the November 24th raid. Desperate ramming tactics, employed by specialized units like the 47th Sentai, resulted in pilot losses without proportional gains against bomber formations. Japanese intelligence services consistently underestimated actual B-29 cruising speeds at 350 miles per hour at altitude. Attempted adaptations included rushed night fighter developments, but severe production delays and material shortages hindered implementation timelines. Overall, defensive measures achieved merely a 1.4% loss rate against B-29 operations through this initial period, completely unsustainable for preventing continued attacks. Japanese aviation industry responded by prioritizing high-altitude interceptor development. The Ki-84 Hayate received engine modifications for improved performance above 25,000 feet. Production shifted toward the Ki-100 Goshikisen, designed for high-altitude interception. Turbo supercharger development accelerated despite technical challenges. Pilots received supplemental oxygen equipment and high-altitude flight training. Tactics emphasized diving attacks to maximize speed advantage. Some units experimented with upward-firing cannon installations. Anti-aircraft defenses underwent reorganization. Additional 75mm and 88mm guns deployed around critical industrial areas. Fire control radar installations increased from 12 to 38 units. Barrage balloon deployments reached 450 around Tokyo. Searchlight batteries expanded to 200 positions. Ammunition production prioritized proximity-fused shells. Observer networks improved early warning coverage. Underground command centers coordinated responses. Fighter production faced critical material shortages. Aluminum allocations decreased 40%. Engine output declined due to ball bearing scarcity. Quality control suffered from inexperienced workers replacing drafted personnel. Training flight hours reduced from 500 to 150 hours per pilot. Fuel availability limited operational sorties. Dispersion of manufacturing to prevent bombing reduced efficiency. By January 1945, monthly fighter production dropped to 1,200 units from 2,100 in mid-1944. Tactical innovations included phosphorus bombing to illuminate night formations, explosive-laden aircraft designated for ramming attacks, cable trailing techniques to snag bomber wings, air-to-air bombing from above formations, coordinated multi-squadron attacks. Most proved ineffective against defensive firepower and formation discipline. Psychological impact on Japanese pilots proved severe as casualties mounted without corresponding success. December 1944 through January 1945, critical industrial targets across Honshu Island. Successive B-29 waves assemble in formations exceeding 100 aircraft. Central fire control systems aligned for optimized collective protection. Japanese leadership expected gradual industrial erosion. United States combat casualties stayed remarkably below 1% per sortie from hostile defensive fire. General LeMay personally oversaw amplified mission operations in revised command instructions. Combat sorties exceeded 100 major raids during this period. Reliable pressurization systems upheld 10-hour mission durations without crew fatigue. Japanese interception operational efficacy lingered at merely 10 to 20% per captured Japanese military documentation. American technological preeminence compelled defensive force redistributions, critically diluting other Pacific theater sectors. Aggregate combat flights surpassed 1,000 individual sorties by early 1945, with 456 probable enemy aircraft destructions. Sustained offensives solidified the fundamental doctrinal overhaul. Concentrated raids targeted aircraft, manufacturing factories in Nagoya and Tokyo, dropping 1,200 tons of high explosives in December alone. LeMay's aggressive tactics emphasized mass formations of 50 to 100 aircraft per individual mission. Japanese fighter losses mounted catastrophically to 200 aircraft monthly, an operationally unsustainable attrition rate that rapidly depleted experienced combat pilots. Critical production facilities suffered cumulative structural damage, with the vital Nakajima Musashino engine plant operating at merely 40% capacity by January. Strategic targeting expanded to include Mitsubishi Heavy Industries plants producing 30% of Japanese aircraft engines, Kawasaki facilities manufacturing Ki-61 fighters, ball-bearing plants at Osaka, oil refineries, aluminum production, shipyards. Damage assessment indicated 35% reduction in aircraft engine output. Fighter production declined 28%. Pilot training suffered from fuel shortages. Replacement aircraft quality deteriorated. Inexperienced pilots faced combat with under 150 training hours. Formation tactics evolved through combat experience. Lead bombardiers received improved training. Pathfinder aircraft marked targets with incendiaries. Radar bombing accuracy improved to 20% circular error. Defensive tactics integrated fighter support when Iwo Jima provided emergency fields. Rescue submarines positioned along flight routes saved 380 downed airmen. Weather reconnaissance flights preceded major raids. Strategic planners identified 83 critical industrial targets. February through March 1945, contested skies over Nagoya and Tokyo metropolitan areas. Japanese adversary aircraft initiate desperate frontal assault tactics, immediately countered by sophisticated mechanized turret responses. Central fire control systems anticipated to underperform against massed attacks instead attained extended effective coverage, successfully impairing 770 attacking fighters. B-29 defensive gunners appeared prominently in comprehensive Air Force combat compilations and awards. Operational system flaws were systematically rectified via simplified procedures, maintained elevated flight profiles effectively evaded enhanced Japanese detection capabilities. Central fire control mechanisms neutralized 714 Japanese aircraft from authorized official combat tallies. Demonstrated proficiency significantly diminished interceptor force commitment, curtailing available deployments. Hostile action-induced casualties amounted to just 147 of 414 total B-29 losses, clearly underscoring mechanical system predominance over actual battle hazards. Defensive collapse signified the operational apex of unforeseen technological impacts. February precision raids inflicted 40% cumulative damage on Nagoya manufacturing plants, with strikes targeting critical machine tool production facilities. Gunner shoot-down claims peaked during massed attacks when tight formations of 80 to 120 B-29s presented overlapping, interlocking fields of fire. The Central Fire Control System's combat effectiveness stemmed from synchronized response times under 1 second, enabling multiple remote turrets to engage single targets simultaneously with concentrated fire. Japanese fighter pilots reported profound frustration in after-action debriefing accounts, noting the tactical impossibility of pressing close-range attacks through the defensive fire envelope. The 50-caliber armor-piercing rounds, delivered at combined rates exceeding 800 rounds per minute per gun position, created zones of lethal fire density extending 1,000 yards from bomber formations. Defensive innovations included improved tracer mixtures for better visual tracking, incendiary rounds for fuel tank hits, armor-piercing ammunition for engine destruction, increased ammunition capacity to 10,400 rounds, improved turret rotation speeds, enhanced optical sights, better communications between gunners, coordinated fire procedures. Japanese countermeasures proved largely ineffective. Armored cockpits added weight-reducing performance. Self-sealing fuel tanks couldn't prevent catastrophic damage. Pilots resorted to hit-and-run tactics, avoiding defensive fire. Statistical analysis revealed defensive effectiveness. 714 enemy aircraft claimed destroyed, 456 probably destroyed, 2,008 damaged, 89% of attacks broken off before reaching firing range. Gunner training emphasized deflection shooting and range estimation. Recognition training prevented friendly fire incidents. Ammunition conservation balanced firepower with weight. Malfunction rates decreased from 12% to 3%. Maintenance procedures improved reliability. Combat experience validated design concepts. March 9 through 10, 1945. Revolutionary low-level transition over Tokyo, operationally grounded in validated high-altitude successes. Lead Pathfinder aircraft designate incendiary objectives, inheriting from precision bombing methodologies. Initial high-altitude approaches proved insufficiently precise against dispersed targets, prompting incendiary strategic adaptations. Core technological capabilities assured mission endurance. General LeMay personally mandated tactical alterations in direct communications. 279 B-29s participated in massive incendiary operations. Proven central fire control systems secured formation groupings during approaches. 665 tons of incendiaries dispersed across 1,595 individual sorties, Operation Meeting House official archives. Pressurization and fire control capabilities affirmed high-altitude operational feasibility, directly facilitating subsequent nuclear weapon applications. Japanese defensive safeguards completely disintegrated, with anti-aircraft effectiveness at merely 10% of German Luftwaffe defensive potency. The operational pinnacle fundamentally reconfigured strategic aviation doctrine. Operation Meeting House incinerated 16 square miles of Tokyo, causing 90,000 to 100,000 civilian fatalities in history's deadliest single air raid. This tactical shift, enabled by complete confidence in the B-29's defensive systems, validated at high altitude, yielded 70% urban destruction rates across subsequent metropolitan operations. The technological foundations established through pressurization and automated fire control permitted aircrews to execute missions at any operationally effective altitude, fundamentally transforming strategic flexibility. Subsequent incendiary raids on Nagoya, Osaka, and Kobe applied identical devastating tactics, with B-29s dropping M69 incendiary clusters from 5,000 to 9,000 feet. The Central Fire Control System, originally designed for high-altitude defense, proved equally effective at lower operational elevations, maintaining adequate protective coverage that limited combat losses to 3.1% per sortie. Incendiary tactics exploited Japanese urban construction, wooden buildings, narrow streets, dense population, limited firefighting capacity. M69 clusters released 47 individual bomblets, creating firestorms. Winds spread fires across fire breaks. Water mains broke from heat. Evacuation routes became blocked. Temperatures exceeded 1,800 degrees. Oxygen depletion caused asphyxiation. Survival rates in target areas reached 20%. Strategic results proved devastating. 178 square miles destroyed across 67 cities, 8.5 million displaced, 330,000 civilians killed, 476,000 injured. Industrial production declined 80%. Transportation networks collapsed. Food distribution failed. Civilian morale deteriorated. Military effectiveness degraded as resources diverted to fire protection. Aircraft production facilities dispersed to 25,000 small workshops, reducing efficiency. Essential workforce killed or evacuated. raw materials became inaccessible. April through August 1945, Pacific theater operations concluding decisively in Hiroshima and Nagasaki atomic bombings. B-29s conclude historic atomic weapon deliveries, sophisticated mechanisms, operational amid extreme operational perils. Japanese leadership envisioned extended defensive defiance. B-29 strategic initiatives expedited unconditional capitulation via complete manufacturing infrastructure obliteration. General Arnold appeared in subsequent strategic evaluations analyzing campaign effectiveness. Technological innovations permitted over 160,000 tons of ordnance released. Combat casualties leaned disproportionately toward non-combatant civilian populations. 414 B-29s forfeited to all causes, with 147 losses to flak and fighters. Strategic Bombing Survey Final Report. Fundamental doctrinal evolution accelerated conflict termination, significantly mitigating projected United States invasion losses. Fabrication disparities, 3,970 B-29s, produced against Japan's exhausted aviation industrial capacity, determined strategic resolutions. Long-term ramifications transformed post-war aeronautical design approaches. Strategic bombing campaigns demolished 178 square miles of urban areas, displacing 8.5 million civilians from homes. Human toll reached 330,000 civilian deaths from bombing operations, with 90,000 occurring in the single Tokyo raid. Industrial capacity declined 80% by July, with aircraft production falling catastrophically from 28,000 units in 1944 to fewer than 3,000 in the first 7 months of 1945. The B-29's technological advantages, pressurization enabling high-altitude operations, and central fire control providing autonomous defense, permitted a campaign of unprecedented scope. Loss rates remained below 4% overall, with 147 aircraft lost to enemy action from 33,000 combat sorties, a sustainability impossible in earlier bombing campaigns. Atomic missions represented culmination. Enola Gay delivered uranium weapon on Hiroshima, August 6th. Boxcar dropped plutonium device on Nagasaki, August 9th. Combined casualties exceeded 200,000. Emperor announced surrender August 15th. Formal signing occurred September 2nd. Strategic bombing proved decisive in ending Pacific War. August 15, 1945, Japanese surrender declarations broadcast nationwide. Vacated operational aerodromes as combat activities halt, compiling conclusive operational assessments. Antebellum strategic doctrines stressed fighter escorts. The B-29 illustrated operational independence through technological advancements. Post-war military evaluators appeared in comprehensive United States strategic bombing survey inquiries. Revolutionary mechanisms shaped jet-age bomber configurations. Aggregate campaign effects encompassed over 500,000 Japanese casualties from air operations. B-29 endeavors proved operationally pivotal in the Pacific, derived from survey conclusions. Unanticipated technological factors compelled Japan's unconditional yield, concluding hostilities. The B-29's pressurization and fire control not merely astonished opponents, but established enduring standards for strategic bombardment. 3,270 exemplars symbolized American manufacturing determination, representing industrial capacity that overwhelmed defensive adaptations. Direct influences extended to Cold War bombers like the B-52, which inherited pressurization systems and remote-controlled defensive armament. Official surveys affirmed strategic bombing's role in economic collapse, averting invasion casualties estimated at 500,000 American personnel and millions of Japanese civilians and military. The technological revolution embodied in the B-29, marrying altitude performance with automated defense, redefined aerial warfare, demonstrating that industrial sophistication could achieve strategic objectives previously requiring mass armies. This lesson, purchased with 414 aircraft and their crews, established principles governing strategic aviation for generations.